The concepts of probability and randomness are likely among the most misinterpreted in mathematics. Strictly speaking, events such as flipping a coin or rolling a dice are completely determined by the initial conditions of the systems, and provided we knew all information available, we would be able to predict the outcome without margin of error. Yet, even when there is no randomness involved, probability theory still gives consistent results when applied to the study of such experiments. In this series of videos, I'll attempt to build a solid basis for the construction of one of the most fundamental branches of mathematics. For starters, suppose we pick a random number between 0 and 1, and we'll call this number x. Now, what would be the probability that x is exactly 1/3? Some of you might already know where this is going, especially if you've taken a probability course before. If not, I invite you to pause for a moment and think about this question. The answer, and the reason behind it, reveals one of the foundational ideas behind how mathematicians understand probability. To get our bearings, let's start by reframing the experiment. Imagine splitting the interval 0-1 into two parts, from 0 to 1/2, and from 1/2 to 1. We're assuming the number is chosen uniformly, that is, every point in the interval is equally likely. Consequently, each region has probability 1/2 of containing x. We'll return to what uniform really means in a future video, but for now, think of it as choosing a number completely at random, with no preference for any region of the interval. In this case, since 1/3 is between 0 and 1/2, we'll focus on this section and consider this new region. Again, splitting this interval in half results in two regions, each with probability 1/4. Since 1/3 is between 1/4 and 1/2, we turn our focus to this interval. Following these steps indefinitely, we can identify two key observations. First, at each step, the probability that our number lies in a given interval is cut in half. If we look at the sequence of probabilities formed, we can analyze its limit, and we find that it converges to 0. I won't dive into the foolproof here, since it falls outside the main focus of the video, but the intuition is simple. By repeatedly dividing by 2, we can make the resulting value as small as we like. In other words, by continuing this process indefinitely, we can get arbitrarily close to 0. Secondly, the process of repeatedly halving the interval produces a sequence of nested intervals, each one contained within the previous. By always choosing the subinterval that contains 1/3, the sequence steadily narrows down around that value. As the intervals shrink, they ultimately converge to a single point, 1/3 itself. This result comes from an important principle in real analysis called the axiom of completeness, which informally tells us that the real numbers have no gaps. One subtle but important detail is that these intervals must be closed, meaning they include both endpoints. This guarantees that the limiting point actually lies in every interval in the sequence. Finally, combining these two observations, and after a bit of hand-wavy but entirely valid reasoning, we arrive at the conclusion that the probability of our number being exactly 1/3 is 0. At this point, you might suspect that nothing about this argument was special about 1/3. We could have repeated it with any number in the interval 0-1, and that's exactly right. The probability of landing on any specific value in a continuous interval is 0. But this raises an unsettling question. After all, once we pick a number, it will be a specific value in the interval. So how can the probability of hitting any particular number be 0? How can an event that definitely happens still have probability 0? Let's begin by laying out a more rigorous framework for how probability is defined in mathematics. Consider an experiment with a finite number of possible outcomes, say rolling a 6-sided die. If we assume the die is fair, then each phase has an equal chance of appearing, in this case 1/6. And because mathematicians enjoy naming things, let's introduce a variable capital X to represent the outcome of the roll. This means that X takes values in the set of integers from 1 to 6. We'll call X the random variable of the experiment, and we'll refer to the set of integers, which we'll denote by omega, as the sample space. Next, we need a function that assigns a probability to each observable outcome. But there's an important detail. We don't just want to define the probability of rolling a specific number. We also want to assign probabilities to events such as rolling an even number, or rolling a number greater than 4. This means we have to consider any combination of possible outcomes. Therefore, the function we are looking for must be defined on the set of all subsets of omega: the empty set, the sets containing only one element, the sets containing only two elements, and so on and so forth. We will call this mathematical object the event space, and the function we keep mentioning will be named the probability function. Together, these three components, the sample space omega, the event space, and the probability function, form what is known as a probability space. It's worth mentioning that, for this system to be consistent, there are some conditions we need to assume. One of them is the domain of the probability function, which in our example was the power set of omega, must be what is known as a sigma algebra. A set F is called a sigma algebra of omega if it satisfies the following conditions. Number 1, omega is an element of F. Number 2, F is closed under complements. And number 3, F is closed under countable unions. Similarly, we have to assume our probability function respects three axioms for it to behave as we expect. Number 1, for any event A in our event space, the probability of A is between 0 and 1. Number 2, the probability of omega is 1. And number 3, if A1, A2, and so on is a sequence of mutually exclusive events, then the probability of the countable union equals the sum of the probabilities of each event. Given these three conditions for our probability function, it's possible to derive useful properties. Just to give a few examples, we can prove that for any events AB, the probability of the union is equal to the probability of A plus the probability of B minus the probability of the intersection, and the probability of not A equals 1 minus the probability of A. Now, there's an important subtlety to address here. Notice how the power set of any set is a sigma algebra, since it contains all possible subsets. However, if omega is uncountable, such as the interval 0, 1, its power set contains far too many subsets for a probability function to be well defined in all of them. To handle this, mathematicians work with smaller, specially constructed sigma algebras. For instance, in the case of the real numbers, we use a set called the Borel sigma algebra. For now, all you have to know about this particular sigma algebra is that it's both small enough for us to meaningfully assign probabilities and large enough to satisfy the three defining properties of a sigma algebra. Up until this point, we have successfully established a solid system to study events such as flipping a coin, for example, where we can define a random variable to take the values 1 if it's heads and 0 if it's tails. The sample space omega would then consist of the set containing 0 and 1, while the event space would be the set containing all possible subsets. Nonetheless, we are yet to determine how probabilities are calculated in the first place. On the next video, we'll take a detailed look into probabilities itself, as well as the concepts that were left unaddressed in this video, specifically the idea of uniformity and the Borel sigma algebras. Moreover, we'll study two of the most important definitions in probability theory: distribution functions and density functions. I hope this video was helpful for those struggling with these concepts and captivating enough for you to stay tuned for part 2. Without anything further, thank you all so much for watching.